Hello, Sean here from SMD Methods. This is now the fourth video in what was to be a three-part series on using an RK4 solver for a second order ordinary differential equation. But again, as things normally do in these videos, the time does go on, and I decided to cut video 3 short after the determination of the MATLAB solution, or the validation completion of our RK4 method using MATLAB. Let's cut it off at video 3 and put in this next part, which is the SimScape version of the solution to a video 4. So let's move on ahead with SimScape and see if we can work out this RK4 method using more of a graphical interface. So what we are dealing with here is a spring mass damper system. We're just limited in the one axis, so we'll imagine this here maybe to be the likes of a vehicle suspension system for argument's sake. So what I'm going to do is open up a library browser. I have SimScape in here. Now typically, you might go looking in, for instance, in the SimScape, we could try the utilities, we could try multi-body, foundation libraries, any of these things here, and pull in from it. So the likes of the translational elements will be found, for instance, the foundation library mechanical, and we also have translational there. But sometimes I find it handier if you just double click into the screen here, and you give the text prompt a prompt, and it might just be something as simple as translate or translation, and it brings us up all our options here. So what we're going to do is I'm going to start off with a ground or a translational reference. So yeah, there's the little bit of browsing if you do it this way, unless you put in the full translational reference. What you can do is, if you recognize the symbol here, it'll be an easy one maybe to find. So I'm going to go with the translational reference on this one. I'll just scoot it in for me. See if we can zoom her in. There's a connection point up at the top. I'm going to go Control R and just spin that around a couple of times. So I can call that transition reference. If I hover over this one here, I could show the block name, and indeed I can call this someone. So maybe just call this a ground. Then I'm also going to have a mass, so I'm just going to prompt mass. There's a mass in here. See if we can line that up there. At the minute, if we connect the mass, what we're going to have is just a suspended mass hanging here off what's really a rigid beam, which isn't what we'll have. What we do have is going to be a spring and a mass connected in parallel, similar to what we see here. So what we'll have here is just spun around by 90 degrees. I'm going to double click on the mass, and I'm going to put in its value. Now what I can do here is I can put in an absolute value of 20 kilograms into this if I like, and that has it connected there. Or what I can do is maybe what the more solid solution would be. If I was to first, let's not waste this, and let's save this. And what I'm going to do is I'm going to save this as numeric MATLAB functions. It's not really a MATLAB function. See, do I have anything in here? Videos, numerical methods, RK. No, I haven't anything saved in there as such. So let's go training, numerical methods. It's not really a MATLAB function, it's a live script. So I'm going to keep it maybe out here. Let's go for MATLAB scripts. And in here, let's call this RK4 spring mass damper, and then go from numerical methods for engineers underscore ed8 underscore prob 25 underscore 16. Now I can't put in these hyphens as MATLAB naming or file naming convention will not allow, and I can't put in, I don't think I can put in full stops or dots. Save. Yeah, I can't use the full stop. I need to put in the underscore. Let's see, can I just put in the underscore there? Underscore, save. Yeah, so the underscore's fine. Can't use the dots, can't use the hyphen. So that's that saved in. So at least I have that. So what I'll do now down here is let me CLC everything here, clear into there, and close this off. Close out. My workspace is fully cleared now. I'm going to start up a new live script, for instance, and we're going to write new values into the workspace. Probably could have used the last one. M is equal to 20. C is going to be equal to 40. And KS was equal to 20. That's really all I need to know, is the parameters of my physical system. I'm going to run that to store the values into the workspace. When I close this down, what I can do is I can just now call up M, and what it's going to do is it's going to read it from the base workspace. So I can change or update my code or run a loop or whatever I like in MATLAB and have the SimScape update accordingly. Now what I also have in here is double click. Let's go for a translational damper. C in an R connection. R connects to the reference frame. So reference is going to be 0. Control R to spin that around. And I'm going to connect that into here. And I'm going to connect that into there. So there is our damper. Double click into the damper. Damping coefficient, I'm going to call C and ask it to pull that up from the base workplace. And you can see it there being prompted as 40, and Newton seconds per meter, them units are absolutely hunky-dory. Let's show that, and let me uncomment that out, and let's call that just damper. Now the next thing we're going to have is a translational spring. And again, what we want to do is I want to rotate that round. I'm going to go Control I is a flip, Control R, reference up to the top. Connect that into there, connect that into there. Double click into this, and my spring rate, spring constant is KS, pulled up out of the base workplace, is 20. Now what I want to do as well is I need to put in a solver block for this, because it will not work without a solver. And put a solver on into here. That's fine. What I'd also like to do into this is I'd like to put on a sensor. I'll need to put in an initial nominal or initial target of this. I know that this is going to be 1 meter as an initial value out of sync. This is going to be stretched by 1 meter, which will drop this down 1 meter below where it otherwise would be. But I also want to put in a sensor as well, so that I can read this out on a scope. Let me just scoot the mug over to that side. So what we want to put in is a translational reference damper, dedent, inverted hard stop damper, spring, translational motion sensor. No, translation, it's really a multi-body interface velocity converters. Transitional properties, just not seeing it there. Let's go on to SimScape. Let's try into foundation library, try mechanical sensors, and I have a ideal translational motion sensor. That's the one that I want. I'm gonna Control R to put the reference on the top, then Control I to put my two sensing variables out here to the right hand side. R connects onto the reference side, C connects on the other side of the damper. I'm going to double click into that. The initial position I know is going to be extended out by 1 meter, so that's important there to know. So when we're setting the initial conditions on this, you set it on the spring, but you also have to set it onto the sensor, because the sensor is the thing that's going to output the positions in P and the velocities as well. So what I'll do is I'm going to run a scope in here and double click into that, and when I can write it into scope, I'm going to go to display grid. I'm going to put in 2 separate sections in that. Let's check my legends settings on that. OpenSim start don't need is a 2-1 grid, all hunky-dory. So I can't connect, I need to make a second connection onto that. Settings, settings, general time axis scaling, number of input ports is 2. That's the one I missed. There's 1 and 2. Now I can't connect that into that because obviously this here is taking a physical signal, which this is a Simulink value into the scope. So what I need to do is I need to take a physical signal to Simulink converter, which is a PS Simulink converter, and I'm taking that as position. Right, so our vector format is position. Autoline root. Okay, let me see. It's going to be, I'll call that X coming in there. And then we're also going to have velocity. Oh, that's coming to another sensor. So if I hit control, if I right click and drag down, it'll create a copy for me. Just going to drag and drop that to there. Dragging that into there. This one here is V. So I'm happy enough with my default units, the vector format, and my output signal unit is going to be meters per second, and that's going to be meters. Okay, and yeah, let's go on ahead and hit a run on that. Oh, I need to do my stop time is 15 seconds, and our current solver is ODE 45, so it's set up on auto. Alright, so let's just see what I have here, and we could see our response starting at our X position, starting at 1, and we're damped off nicely to there, and then our velocity drops down to just above minus 0.4 before it settles off, and that's running with ODE 45. What I should have did was I should have outputted my graphs there from video 3 on the MATLAB, but maybe just take my word for it that it looks pretty good, like what it should be. What I'm going to do is I'm going to change my C value here to underdamp it to 5. I'm going to run this to overwrite the value in the workspace. Come back on into my scope and let's just run it here. And there's our oscillatory system on our underdamped system, our underdamped setup, which looks correct. Now, thing that we're doing is we're running ODE 45, so we're not comparing apples for apples. What I'd like to do is run this using classical Runge Kutta. So there's a couple of ways to do this here. You can go into your modeling and model settings in here, and you can change your solver in there, but the quickest way, the way I always do it, is I click down to the solver selection down here in the bottom right, and then you have your different options in here. It says solver ODE 45. You have solver settings, right, which is the gear, right? The accept suggested settings, sometimes they'll come up whenever we run this this function here, which is the profiler. But at the minute, what I'm going to do is I'm going to change this using the gear to Runge Kutta 4. So the automatic solver selection in this one selected ODE 45, which is a Dormand-Prince solver, which is variable step. I will not see RK4 in this. Dormand-Prince is the ODE 45 because RK45 is not a variable step type of solver, it's a fixed step. So I change that to fixed step. Right? What I will see in here now is Runge Kutta ODE 4. Right? So that's fourth order. These are all Runge Kutta. There's Euler's, Heinz in first order and second order Runge Kutta, but Gaki, Champion in third order, and Runge Kutta 4, which is classical Runge Kutta. I'm going to select that there. 15 is our stop time and our step time. Fixed step size, fundamental sample time, that's given in there as auto. We can put that to 0.2 here if we want. I just want to double check to see if I ran I didn't know if this actually comes through in 0.2. Take off the space there. Let's rerun that and put H into the workspace. Can I select H there? No, I didn't think that I could. I'm going to put a 0.2 there, apply that. Okay, so now we're running Runge Kutta 4. And just run it from the scope, and let's run that out again. And there's our step, so it looks nearly identical, same. So you'd say, well, should I run Runge Kutta 4 or ODE 45? Should I use a fixed time step or use the defaulted ODE 45 Dormand-Prince variable time step solver? Well, there's metrics that we can do to determine that. But first what I'm going to do is I'm just going to return this to my critically damped damping coefficient of 40, rerun that step to update my workspace. I'm going to rerun this again. So back onto a critically damped profile. If I X out of that, if I go down to ODE4 here, which is Runge Kutta 4, classic Runge Kutta, and I run the profiler. Just give it a second there to open. Okay, and now if we run this here, 0 to 15, keep the buffer where it is. Right, this will run and it's going to give us HIPAA statistics here. Now, one of the main statistics that I like to look at this here is the runtime. So the run and the total steps. So obviously it's going to be 75 because we're using a step size of 0.2, which is 1/5 of a second, and we're running for 15 seconds. So our run per simulation time ratio, 7.88 E to E of -3, and a runtime of 0.12 seconds running ODE 45. So if I was just to take a note of that for myself, if I was curious to see what is the more efficient solver for a system like this, I would write that RK4 had a runtime of 0.12, and if I was so interested over the simulation time ratio for modeling purposes, I would also take note of that. But it's adequate here. Let's just have a look to see how long these two solvers took to run. We could also look at, there was one here for a computational effort, I did think. Average step size, max step size, usage. No. Let's do the run. I was near sure that there was another metric that I had used, or that I used to check. Maybe not. Ratio. If you are aware of it, certainly please enlighten me, because I, for the life of me now, just cannot remember. But I'm going to take the run over the simulation time ratio as well. Now, if I was to, and no issues found in the model, everything looks good. If I was to change this back to ODE 45, I have to move the mug over to the side again to access the menu. And we went back to a variable time step, left it to auto, or else go to ODE 45, right, which is the one that it did use. Obviously, it's going to automatic the time step in that. Apply, okay, and back into our scope. Move the mug back to this side, and we'll run that again. So it looks identical, same. So as far as we're concerned, the two of them return the same result. But how much effort, how long has it taken to return the same result? That's the question. So what I'll do is I'll just X out that, move the mug again, ODE 45, I'm going to go to the profiler here, double click, click that once, I'm going to run here, move the mug over to this side, and let's have a look at what we have. So see it here now. So for the ODE 45, which is Dormand-Prince, a variable time step, the runtime is 0.08 seconds, right? Which is 2/3, yeah, 2/3 of the time that it took to run the RK4. So it runs it much quicker, and the run per simulation time ratio at 5.47 e to the power -3 is superior to the 7.88 e to the power -3 of RK4. So the during simulation solver, use the maximum step size total. You can improve the simulation speed, increase the maximum step size in the solver pane. Now, I was sure that we had it as selected it as auto in ODE 45, but there's giving me a max step size of 0.3. Here it's saying I could actually make that a little bit bigger. Obviously, at that damping ratio, there's very little happening here, and a larger step size there actually could help. So I was using 0.2 as my fixed step size in in RK4. According to this here, if I make my step size somewhat larger, right? When we talked about this in video 2, what's an adequate step size? It says let's try 0.2 for RK4. Maybe we could try 0.25, 0.3. What that would naturally do would bring my runtime down, and would bring RK4 more into the Dormand-Prince ODE 45 sort of a range. Now, how would you know to do this prior to running the SimScape model? Well, you wouldn't, not that I know of anyway. But certainly whenever we use SimScape for modeling, we should not just really be using it for replicating what MATLAB can do. Albeit we didn't write one equation in here and this solved it for us. It's that versus this, and that's only from 0 to 0.2, whereas this here is from 0 to 15. It's much quicker, obviously, but using the likes of the solver profiler gives us a much more, I suppose, deeper, more kind of information yielding insight into how the solver works and the most efficient or the best settings for the solver. So yeah, just a couple of things there that might be worthwhile taking on board and worthwhile exploring. Now, what I did do was I had closed the let me just open that up there again. There it is there. So see here, this 0.3. I wonder, I'll tell you what, I probably should be able just to overwrite all that again and just maintain my values. So I should. That all should be good. At 0.3, C is equal to 200. Put C back to 40 for this one here. And we're back to that again. So that's at 0.3 as a step size. If I bring this here to just when you thought the video was going to end, I'm going to configure ODE variable step, fixed step, Runge Kutta 0.3, play, okay, scope, run. So we're comparing them two again. Them two there. Looks a wee bit different. Let's just get this one here maybe to pop out. So the top one is velocity. Same as our bottom one here. Right, so I could have made that maybe just one much larger scope. Check it. Run the call with 0, 0, then 0.1 coming up, 4, 5. Obviously this one here could do with getting stretched out an awful lot more to make it similar to what's in the scope, given that the scope is narrow. It's more like that. I'd be happy enough that they're equivalent. It's really 10 before it starts to flat out at 8 before it flats out. Yeah, they look good. So I'm happy enough with velocity. This one up here is position, where here this is my position. So get my SimScape behind that. There's position. Yeah, so they're the same as well. Okay, so I haven't done that. I'm going to X out of that, drop that back, drop that back. I'm going to come into here. I'm going to go into my solver profile for a fixed step size of 0.3. Solver profiler. Eventually might open. Try again here. Run ODE solver profiler. Oh, just the word, they're open away there in the background, announced to me. Wouldn't be the first time that happened. There it is there. So max step size is 0.3. What we're going to do is going to have to rerun this to update it because this was still from the last one. So here the runtime has been brought down to 0.8, which is the same as ODE 45 using a 0.3 time step. So yeah, there's not much on the difference of it. So if we weren't going in to analyze and to tune Runge Kutta 45, specifically the time step of it, using the automatic solver, obviously in SimScape as part of the MATLAB package would be probably a better way to go. It's not any less efficient to use ODE 45, so any sort of additional computational effort that would be involved in deciding should the step size come down and the step size should come up appears here to be relatively negligible, albeit I still am nearly sure that I had a solver OD for you, that there was a metric which told me about the computational effort that went in, but maybe not. But anyway, yeah, that's all I was really wanting to show on the SimScape side of this. Of course, you can do this in Simulink as well, and set up the integrators and set up the error loop and run it through that way. It's a nice way to set it up. I could, if you want me to do a video on that, absolutely. Just let me know. Put it into the comment there. Tell me, Sean, let's do a video on the Simulink setup of this as well, and then at least you'll have the MATLAB, you'll have the coded solution, you'll have this this physical interpretation, the hardware solution to it, and then also the symbolic math solution to it as well. The kind of the loop, the workflow, if you like, progression through the mathematical functions that Simulink gives you way to do it as well. So yeah, thanks very much for this. I'm going to conclude this 4-part series now. I hope you have taken a little bit away from it and maybe gained a deeper appreciation for the Runge Kutta method, especially notably Runge Kutta 4. And I hope maybe you found some inspiration in places that you can apply Runge Kutta 4 for solving not only now first order ordinary differential equations, but also second order ordinary differential equations. So if you haven't already, do hit the subscribe button, and I'll just keep putting on content into this channel itself with respect to numerical methods for engineers, but also in the other playlists onto the channel, which include CFD, PLCs, automation, and other aspects and fields of interest to mechanical engineering. So as always, thanks very much for coming on into the video, and yeah, let me know what you think. Thanks very much.